Welcome back. This is the Day the Lord's Made. Bless your be glad in it. In this video, I'm going to talk about general knowledge about voltage and resistance, as well as power and the kilowatt hour. So there are three main things to be aware of here to start: voltage, current, and resistance. So voltage, you should think about voltage as being the motivation. What is going to motivate the electrons to move? We've seen this equation before, but it was a little different. So here we see the units voltage is joules per coulomb. We saw before as work equals Q times V, but again, joules is work, so V voltage times coulombs charge would be the same equation, but voltage is measured as far as how much work does it take to move a certain charge across a place. So if it takes 1 joule to move 1 coulomb, that's 1 volt. So the bigger the voltage, the harder it is to move, or the more energy released as the charge moves. So for you, the most important thing to remember is voltage is a motivation that's going to cause electrons to want to go somewhere. In our houses, our outlets provide 120 volts of motivation. A typical battery produces like 1.5 volts. So the outlets provide a lot of motivation. Current is then how much actually moves along. So current, we measure this in amps. Now, again, as mentioned in previous ones, an amp is a lot of electrons, because an amp is 1 coulomb per second. So if 1 coulomb of charge moves in a second, that is 1 amp. And again, each electron only has this tiny charge right here, so that's a lot of electrons. We should mention real quick that with current, the electrons that move don't move very far at all. They actually just move a little bit. Their net velocity or their drift velocity is very tiny. So it's not like the electrons from the power plant come to you. When you have electricity moving through something, the device provides its own electrons. And since we actually use alternating current, it doesn't go anywhere. More on that later. So voltage is the motivation. Current is how much actually moves, how much charge sets move. Resistance, you should think about resistance as being the anti-motivation. We measure this in ohms. It's how hard is it for the electrons to move through something. Again, in general, metals are conductors, therefore they have low resistances, very little. Power lines, just because they're big, have some resistance, but in general, most metals have very little resistance towards electrons moving through them. Insulators have a large resistance. And it always amazes me when I think about plugging something into the wall, and there's a little layer of plastic. That little layer of plastic that's around the copper wire keeps you alive, because that little like millimeter thick of plastic around that copper wire provides enough insulation that no energy leaves the line. And so resistance for metals, really tiny. You should be thinking like micro ohms. Resistance for things like your skin, resistance for things like plastic, you should be thinking like giga ohms or tera ohms or mega ohms. There's a huge change in resistance. So resistance also is the idea that as electrons move through someplace, they just get less motivated. So you can think about the amount of current then being equal to our ratio between the voltage and the resistance. So again, if we rearrange this equation here, we see that resistance is change in voltage divided by current. If we rearrange this, it'd be current equals voltage over resistance. How motivated are the electrons? How much resistance is there? So then putting these things together, we get power. Power is, again, how much work gets done. So, and a certain amount of time. So it's based off two things: the current, which again be how many electrons are moving through the area, and how much voltage they have. So if there's more motivation, they get more work done. If there's more current, they get more work done. And so we measure power in watts. 1 watt is 1 joule per second. So again, big idea. Voltage is motivation, resistance is anti-motivation, currents, how many are motivated, and then power is just a result of, well, how much motivation do they have and how many showed up to help out. So you can think of this like getting ready for a dance. If you have to like decorate everything and you're part of student council, like, okay, well, we need to get people here, so we got to motivate people to want to help, and then the amount of work you get done, how fast it gets done, depends upon how motivated those people are and how many showed up. So, and that's this idea here. Current is just voltage over resistance. Now, there's other things you should be aware of, like fuses and circuit breakers. So when electrons start moving through someplace in large bulk, what can result in happening is that metal can get really hot, because it's like just inviting a lot of people onto the same road. It's like road rage. So as more people come in to the highway, the road rage increases and it gets hot. And so we have fuses and circuit breakers to make sure we don't have too many electrons moving into a zone. So typically a fuse or circuit breaker is rated at 20 amps. So if more than 20 amps start coming into a single line, it'll shut it off, saying we got to close this down, because even though the copper wire won't catch fire, the things touching the copper wire might. So again, if you think about how your house is built, behind the drywall, there's a whole bunch of copper lines that are just connecting the main power grid to your house. And when you plug something in, electrons, they're not really moving, but this idea that electrons are swinging back and forth in those lines. And if they're touching wood, they likely are, that wood could catch fire if the metal gets really hot. Two different types of current. There's direct current and alternating current. Direct current is when electrons go one direction. This is pretty much batteries. And most devices run on direct current too, and they have diodes that actually make the electrons turn to one direction. More on that later. But there's direct current where electrons go one direction, and alternating current where they go back and forth. And that's what our outlets provide. So in reality, the electrons that are coming in to your house, they're not really coming to your house. The electrons in the power lines don't go anywhere either. They just stay there. They just wiggle back and forth. Because what they're doing is a change where the motivation is. So think of it like a carrot for a horse. You're just like, here, carrot over here, and then like, oh, carrot over here, and then, oh, you keep changing, where do you want to go? And so electrons never go anywhere. They just kind of wiggle back and forth, never getting anywhere. All right, so that's the big difference in direct current and alternating current is which way the electrons go. Direct current one way, alternating current back and forth. All right, now a really important thing for you is the kilowatt hour, because the kilowatt hour is how you're going to be charged in the future when you actually own a house or you're paying rent and you got to pay for your utilities. The kilowatt hour is a unit of energy that we charge people by, because people use a lot of energy. And if you think about a typical light bulb, if you have a 60-watt light bulb, that means every single second that light bulb uses 60 joules of energy. You leave the thing on for a minute, that's 60 times 60, that's 3,600 joules. That's probably on more than a minute. And so you can see that the number will get really large. Your utility bill wouldn't make any sense to you if every single time you got the bill, you're like, wow, I used like 100 billion joules of energy. It'd be a really huge number and people wouldn't know what's going on. So we use this idea of the kilowatt hour to help people know how much energy they're using. It's calculated just as it said, because it's for the consumer. 1 kilowatt hour is 1,000 watts run for 1 hour. So if you have 1 kilowatt device running for 1 hour, you get 1 kilowatt hour, which is 3.6 million joules of energy. On a side note, our body uses approximately 8.4 million joules of energy per day. So we'd get by with 2 kilowatt hours. If you could plug yourself into the outlet, you would just need 2 kilowatt hours worth of energy, which would be pretty cheap. So an example of this would be, what if you have a 100-watt light bulb run for 10 hours? How many kilowatt hours does this use? Well, you got to turn the wattage into kilowatts. So that's divided by 1,000. 100 watts is 0.1 kilowatts. The kilowatt hours is just kilowatts of the device times hours run. So we have a 0.1 kilowatt device running for 10 hours. That is 1 kilowatt hour. Here in Nebraska, that costs you about 10 cents. So again, my body, I would use 2 kilowatt hours per day. So it would cost me about 20 cents to power my body if I could just plug myself on the outlet. And this is probably the most important thing, and you'll see this once a month on your utility bill in the future. Big things at your house that use a lot of kilowatt hours are your dryer and your light bulbs. Typically in America, about 10% of your energy is light bulbs. And on Saturdays and Sundays, when it's laundry day, your dryer and your washer, which are, well, not your washer, but your dryer is an expensive device, just like your oven. They use like 3,000 to 4,000 watts, so they're using 3 or 4 kilowatts hours per hour. So one last thing here for this one is the Electron Volt. I know I've talked about this before, but it's worth mentioning again. So we talk about energy. 1 joule is a lot of energy for an electron to handle. And so we talk about energy for electrons, we use the Electron Volt. So again, before we had this equation where the volt work is equal to the charge times voltage. Well, we small scale that down a little bit, and the Electron Volt is talking about moving just 1 electron by 1 volt, which means that like with a battery, if you have a 1 volt battery, that 1 volt gives every electron 1 electron volt worth of energy. So the actual energy is equal to the charge of the electron, 1.6 to the -19th joules. So again, the Electron Volt is useful for talking about small scale stuff for energy, because an individual electron doesn't store a lot of energy, but in bulk, they do work for us. All right. Your device at your house, they don't run off just one electron doing work. They run off of bazillions of electrons. So on your outlet, you can think of it, the outlet providing each electron 120 volts of electron volts of energy. So again, we use electron volt just on a small scale to talk about energy for an electron. God's peace.